Thank you. Good morning, guys. My name is Colin Joseph from Mexico VPN team, and I'll be your host for the site-to-site IPsec VPN training. First of all, I know we have some folks here from SD1, and I know in SD1, the term VPN is a little bit different, and that I would say it's more similar to what is VRF for us. So I'll try to do my best in order to avoid using the term as much as I can to avoid any confusion. With that being said, that will be our agenda for today. So we'll start talking about site-to-site IPsec VPN, and then we'll talk about ESP versus AH, and then we'll proceed with talking about IKV1 overview, and then we'll talk about IKV2 protocol overview in comparison, and then we'll have a live troubleshooting demo, and after that will be the summary. So first of all, there are two types of VPN, which are remote access VPN and site-to-site VPN. But in this session, we're just going to focus on site-to-site VPN. So we're not going to talk about remote access VPN. And site-to-site VPN is a connection between two or more networks over internet. And it uses IPsec protocol and leverage the benefit of IPsec to provide confidentiality, data integrity, authentication, anti-replay, etc. And it includes topology like DMVPN, GetVPN, and FlexVPN. Just before we jump to ESP versus AH, then ESP is for encapsulating security payload and AH is for authentication header. I think it's really important to talk about IPsec. So IPsec is a security architecture developed in 1998, and it describes how to protect IP traffic over an insecure network like internet. IPsec provide confidentiality, integrity, authentication, anti-replay, etc. So first of all, I want to take some time to talk about confidentiality and data integrity because most of the time, some people are still confused about those terms or at least not able to know what is what. So for example, and the term confidentiality referred to the fact that the data is encrypted and that only authorized user is able to access or read this data or see this data. Meanwhile, integrity is just a way for us to prove or to verify that the data hasn't been corrupted or modified on the path. I think maybe it would be easier if we use an example. So for this example, I'm going to use a website. It's not a Cisco website, and again, it's just for the purpose of this demonstration. So let's just use this website here. First, let's start with the integrity. So as I was explaining, integrity is just a way to prove that data hasn't been modified on the path. And normally we use hashing algorithm like MD5. D5 is not secret, so let's say SHA can be either SHA-1, SHA-256, or SHA-512, it depends. So for this demo, I'm just going to use as data a text. So this text as we're saying here, which is welcome to the site-to-site IPsec training session. So what integrity does for us is that we generate a hash code with the data. So the hash code is unique. So in this example, I'm just going to use a text, but again, it doesn't have to be a text. It can be a software image. So just to show you. So basically, we take the text and we use the hashing algorithm. In this case, we're using SHA-1, and then we generate the hash code. This hash code is unique. So if, for example, right now you can see that's my message, and that is the hash code, right? As you can see. So just pay attention to that. Anything that's changed on this data. So right now, let's just remove a space. Okay, maybe not here. But, or let's just, for example, at the beginning, we have uppercase W. Let's use a lowercase w and generate it again. And it should be different. So anything that will remove or replace in this data, it's going to generate a different hash code. So this is how we're able to verify that this data hasn't been corrupted or there was not a man in the middle who take the data and modify it. So this is how that is the idea of integrity. And if you guys are used to download iOS image from the Cisco portal, so when we download this image, normally Cisco give us like a MD5 hash and a SHA hash. And from the iOS CLI, there's a command which is verify, and then we can verify if the image hasn't been modified or corrupted. I mean, again, if we download it from the Cisco portal, there's no chance that it's been like changed, right, or corrupted. But this is just a way for us to verify that this data hasn't been modified. Again, it doesn't have to be a text; it can be a file. But in this case, I'm just using a text to show you. So that is for the integrity part. I mean, just a way for us to verify that the data hasn't been corrupted. And how do we do that? We use a hash code. So basically, we take our text or data. In this case, it's the text. We generate the hash code. And as I mentioned here, anything that we change on this data, we generate different hash codes. So, for example, if I remove the comma at the end and generate it, it will be something else. Or if I change it to let's use this one. So anything that we change is going to be different. So that's the idea of integrity. As far as encryption, encryption is just a way for us uh, to only give access to authorized user. So basically, the data is encrypted, and we can use like encryption algorithm, symmetric encryption algorithm, like AES, DES, etc., or symmetric encryption algorithm. And the difference between symmetric encryption algorithm and asymmetric encryption algorithm is just with symmetric encryption algorithm, so we use the same key to encrypt the data and to decrypt the data. Meanwhile, with asymmetric, we can use one key to encrypt and the other key to decrypt, or the reverse. So basically, in this one here, in this example, I'm going to use the same text again. Let me just take my text from here. Okay, it was at the end. It was Control A, Control C. Again, it doesn't have to be a text. Like it can also be a file. But in this demonstration, I'm just going to use a text. So that's our data. And right now with this test, we're using a symmetric algorithm, which means we're using the same key to encrypt and decrypt the data. Let's say as the key, we're going to use Cisco. So that is our key. So if I take this data here and I encrypt it, so that is our encrypted text. So I'm going to copy this port here. If I send this data to someone, unless that person has the key, it will not be able to decrypt this message. So that is why we're saying that only authorized users are able to see the data. So let's suppose, okay, let me just change the password and let me hit decrypt text. As you can see, the text is not decrypted because the password is not correct. So let me copy everything again. So that was our encrypted data. Let's use the correct password and it decrypt text again. As you can see here, as soon as I use the correct password or the correct key, then we can see the data. So that is the idea behind and this one is for confidentiality and that is the encryption. So that's the idea behind confidentiality. And this part here is the idea behind integrity. So basically with integrity, just a way for us to prove that the data hasn't been modified or corrupted on the path. Meanwhile, encryption or confidentiality, sorry, refer to the fact the data can only be seen by authorized users. And also with integrity, sometimes you can also use what is called HMAC, which is hash message authentication code. The idea is the same, but beside of just taking our data and using a hashing algorithm like SHA-256 or MD5, uh, we also use a key. So basically, let's see if we can do it from this page also. We should be able to. So basically, it's the same thing. So it's going to generate a hash code for us. But in order for the person to be able to generate the hash code, beside using the hashing algorithm, we also have to use the same key. Otherwise, it will not generate the same hash code. Maybe not this page. Does it have it? No, I'm not seeing it. So, but that is just the idea behind HMAC, which is hash message authentication code. Um, so I haven't found it on this page. I'm not going to pay too much attention, or I'm missing it. So that was just to talk about, to explain what is confidentiality and integrity, because it's really important to be able to make the difference. And authentication, I think most of us are used to that. It's just a way for us to prove our identity. As an example, for example, right now when we are, for example, right now, I guess if we're using the Cisco PC, right, to attend this meeting. So once we power on our PC, we have to put our credential, our credential, right, or our password. So by putting our password, we're proving that we are uh, we are the owner of the PC. So it's authentication. Again, there could be many examples for authentication, but that is just one of them. So let's keep on. IPsec overview. So IPsec include many protocols like ESP, which we'll talk about later, and IK, which is Internet Key Exchange. There are two versions of those. There's IKV1 and IKV2. We have AH, which is authentication header. We'll see it later. So ESP versus AH. Again, ESP is encapsulating security payload, and AH is authentication header. So ESP is defined in RFC 2406 and it uses IP number 50. And ESP provides us data integrity. Again, as I explained what data integrity was. So basically, as it's saying here, just a way to ensure that data has been corrupted on the path or modified by either man in the middle attack or someone is doing eavesdropping and modify this traffic. So it's providing data integrity, authentication, anti-replay, and confidentiality. Meanwhile, with an authentication header or AH, it just provides data integrity, authentication, and anti-replay. Which means if we're using AH, and let's suppose we're sending like telnet traffic, as we know, telnet's not secure, right? So if we're just using AH, so the data integrity, we'll have like a hash code to prove the data hasn't been corrupted or modified on the path, but it's not going to provide us confidentiality, which is the most important part, which means this data encryption is not going to be encrypted. So any attacker or any user who's doing some man in the middle attack will be able to see this data. And that is why in most of our network today, it's normally we use ESP instead of AH, because ESP, besides of providing all the things that AH provide, it also provides us confidentiality, which is the most important part, which means that the data is encrypted. So that is the difference between ESP versus AH. And I gave you an overview. So again, IKV1 is a protocol used to negotiate and create and manage SA, but SA is Security Association. It's also in charge of key exchange and peer authentication. IKV1 is divided into phases: main mode or aggressive mode and quick mode. It's recommended to use main mode instead because it's more secure. And also during this presentation, we'll focus more on main mode. We're not going to talk too much about aggressive mode because it's not secure, it's not recommended. And during the negotiation for IKV1, we normally use UDP 500 and UDP 4500. So the thing is, we will use UDP 500, and if we determine that one of the peers that are negotiate the VPN tunnel is behind NAT, then we will switch from UDP 500 to UDP 4500. Again, as we were saying, right, there are two different modes for phase one: main mode and aggressive. We're just going to focus on main mode because main mode is more secured, and with main mode we have like the negotiation consists of 6 packets. Mostly the phase one consists of 6 packets, sorry, and aggressive mode I believe it's just 3 packets. And something really important, the phase one is just well, we're going to important here. When we're talking about the negotiation, it's a communication between two devices. It's a communication between two devices. So one is acting as initiator and one is acting as responder. But what's interesting, the other person, in this case, the router, right? The other router to respond. So it's not just one person is talking and without the other person saying anything. So for right now, we're going to review the phase one, which is with main mode. Again, as I mentioned previously, it consists of 6 packets. And what's really important to take is that one a router says something is expecting a response from the remote router. So the 6 message in phase one, MM1, MM1 and MM2, this is where they negotiate the
Your audio is... Can you hear us?
acronym here, H, the H A G L
Carlos?
E.
Carlos?
Yes.
Can you repeat again the last 1 minute, please? Your audio was breaking up.
Yeah, sure. So we were just talking about the with Ikevion, there are 2 phases, which are phase one and phase two. And the phase one can be either main mode or aggressive mode, and it's recommended to use main mode because it's more secure than aggressive mode. And main mode consists of 6 packets, while aggressive mode is about 3 packets. We're not going to focus on aggressive mode in this session, but just on main mode because it's the recommended one and also is the most secure. During the main mode, as we were mentioning, it's 6 packets.
Hello, Carlin.
Yes, go ahead.
Uh, could you describe why aggressive mode is not considered to be secure compared to main mode?
Mhm. And I will answer with a lot of pleasure. Is that okay for you?
I'm sorry, I lost your voice. That's why.
No problem. At the end of the session, we'll have a Q&A session, and during this time, you will be able to ask your question. Is that okay for you?
Yeah, sure, fine.
Okay, great. So as I was saying, during the main board, there are 6 packets. And again, something really important to take into consideration here, it's a negotiation. I mean, it's a communication, which means basically when one end is saying something, is expecting the remote end to respond. So the phase mode, the main mode consists of 6 packets. During the MM1 and MM2, this is where the peers negotiate the ciphers. And one easy way to remember this is the famous Hegel. I mean, basically, H is for the hashing, like MD5, SHA-1, SHA-256, etc. And A is for the authentication, basically mean how we're going to authenticate the peers. So it can either be, for example, pre-shared key or RSA signature. And the G is for diffie-Hellman group, which if you're using diffie-Hellman group 2, group 5, group 14, etc. And the L is for the lifetime, and the E is for the encryption. And we can use like AES, DES, triple DES, etc., AES, GCM, etc. And so when the initiator we send the MM1 is expecting the responder to respond with MM2. Remember, again, it's a negotiation, it's a communication. So once an MM1 and the responder send the MM2, which is a reply. So basically what's going to do, the initiator will send those ciphers on the Hegel. So it will send all the cipher, the hashing, the authentication method, the defilement group, the lifetime, and the encryption. And the responder is going to check to see if it's finding a match in his running config or in his database. And then if it finds a match, then it will send a packet. Basically, it's like a payload. Like it will be a thumbs up, like everything is okay. So we can move to the next messages. So once we have phase one pass, then we have phase three and phase four. Um, During phase three and phase four, this is where they're going to negotiate the NAS discovery and also the defilement exchange. Or during the defilement, they will just generate like uh, a secret key. So during the main mod, so the initiator again will send the MM3, which is the first packet for I mean from the initiator, right? So first they send the MM1, which is where they negotiate the ciphers, and the responder send a reply, which is MM2. Then the initiator send the MM3, which is where they negotiate NAS discovery and the defilement exchange, and then the responder will send MM4. Basically, if everything is okay, then it will just send thumbs okay. We can keep on with the next messages. And during the MM5 and MM6, this is where the peers are going to authenticate each other. And something really important to mention here, during MM3 and MM4, the unit is secret key, and the next message will be encrypted. So MM5 and MM6 will be encrypted. So during MM5 and MM6, so the initiator and MM5 will send his identity, and the responder will check his warning config to see if it's finding a match for this identity and see how to authenticate this peer. So if we are using authentication key, if we are using, for example, pre-shared key, so it's going to check in his warning config to see if we're finding a pre-shared key for this identity, and then it will send the reply. So MM5 and MM6, this is for the authentication. And MM1 and MM2 is for where they negotiate the ciphers. MM3 and MM4, this is where they negotiate the NAT discovery and difficultment. And MM5 and MM6 is where they negotiate the authentication part. So that is for the phase 1 and main mode. And for the phase 2, again, during the phase 2, this is where they're going to negotiate the tunnel for interesting traffic or encryption domain. Interesting traffic or encryption domain is just a way to say what are we going to send or which traffic we're going to encrypt and send through the tunnel. So this is something. Some say, I mean, if you hear like encryption domain or traffic selector, it's the same thing. It's just a way to say which traffic we're going to send for the VPN tunnel, like the data plane, basically. And I gave you on the phase 2 is also called quick mode. Sorry, it's a full packet exchange. Basically, during the negotiation, they're going to determine which traffic to encrypt, which is the encryption domain or traffic selector, how to encrypt this traffic, and how to which integrity they're going to use. Basically, we're going to specify that in the transform set. So again, it's called quick mode. So the initiator will send the QM1 setting the transform set. Transform set is where we're going to tell about the hashing cipher, what we're going to use for integrity and for encryption, and also the traffic selector, as I mentioned, or encryption domain. This is just the traffic we're going to send for the VPN tunnel. And if they're using defilement again, which is like if we have to speak at defilement again, then we're doing PFS or preferred secrecy. And we send, the initiator sends this packet, and the responder will respond, and then the initiator will send an ACK. Again, it's a communication. So when one sends something, expecting the mobile device to respond. So that's the negotiation for the for IKV1. Right now, we're going to go over IKV2 protocol overview and comparison. Again, IKV2 is defined in RFC 7296. It's more secure than IKV1 and also support next generation encryption, or should be like AES, GCM, SHA-112, etc. And also with IKV2, for example, we don't have to use the same authentication mode. So basically, we can do, for example, pre-shared key on one side and RSA signature on another side, or EAP on another side. And also it reduces latency, sorry. And that is the negotiation for IKV2. Again, with IKV1, if you remember, we have we're using main mode, right? So the first one is 6 packet, it's MM1, MM2, MM3, MM4, 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 MM5, MM6. And then we have the phase 2 or quick mode, which 3 packets. With IKV2, it's only 4 packets. So basically, the first 2 packets is, I would say, it's like it's equal from M1 to M4 in IKV1. So on the first 2 packets of IKV2, this is where we're going to negotiate the parameters that we negotiate from M1 to M4. If you remember, those parameters were the famous Hegel, right? Hashing, authentication, group, lifetime encryption, and also the defilement group and the natural reversal. So those four first packets in IKV1 are equals to those first 2 packets in IKV2. So the same parameters here are being negotiated, as you can see. Negotiate crypto settings, secret key change, that's the defilement part. And also NAT detection to see if one of those peers is behind that. And the next 2 packet is equal, what I would say, from MM5, MM6, and also the quick mode message, because with IKV2 basically on the next 2 packets is where we're going to authenticate the peers, but also negotiate the child essay. The child essay on IKV2 would be equal like the quick mode. This is what we negotiate like the traffic selector or the encryption domain. So the same thing. So in IKV2 we use the less packet to do the same thing with IKV. But again, the idea is the same. Both IKV1 and IKV2 is doing the same thing. It's for the same purpose, but IKV2 is more secured. It's using more packet to do so. And also with IKV2 we have some more stuff. For example, with IKV2 we don't have to use the same authentication method on both ends. So one end can use pre-shared key while the other one can use RSA signature or EAP. So we will see that's a comparison between the negotiation from phase one. Sorry, this one is for version one, IK version one, and this one is for IK version two. Again, we can see here it's around, let's say 2, 4, 6, around nine packets, right? While with IKV2, just 4 packets. So the first two are equal to the first 4 in IKV1, which is MM1, where we authenticate, where we negotiate the ciphers, the famous Hegel, and then MM3 and MM4, where we negotiate the not transversal and also the difficult element. And then MM5, MM6, we authenticate the peers, and then the quick bond. This is where we negotiate the phase two, right? Which traffic going to send for the VPN tunnel. So those 9 packets here are equal to 4 packets in IKV2. And then as I was explaining, the phase two, like in IKV2, is called chat essay. And just in comparison, right, for the phase one, if we compare it from IKV1 to IKV2, from IKV2, it's called init essay, and the phase two is called chat essay. So this is where again, we're doing the same thing. We negotiate the transform set. The traffic selector or encryption domain, again, traffic selector or encryption domain is the same thing. It's just a way to tell or which traffic are going to send for the VPN tunnel or the data plane. And right now we're going to do a demo. And again, this demo just more for live troubleshooting, so it's not about configuration guide. And for this demo, I'm going to use GNS3. But guys can use any other software that you just GNS3 just a lab simulator, right? So that will be our lab for this demo. And we're just going to focus on IKV2 and not IKV1. Again, we're not going to focus too much on the configuration, but more seeing what's happening during the establishment of the tunnel. So that's our main goal here. And for this demo, we have around 3 routers. This one here is also a router. I just changed the symbol. If you guys are familiar with GNS3, for example, on this one, what I did is I just went to change symbol, and from the classic, okay, I have to wait. You look for cloud or you search for cloud, and then you just change the name. But those 3 here are routers. So I'm using 3 routers and then 2 layer 2 switches and then 2 hosts. So basically what I did is I changed the symbol to this one, which is a cloud, and then I just changed them. But again, all those devices here are routers, and those 2 are switches, of course, and those are some hosts. So let's go to the CLI. Okay, we have to wait a little bit. Thank you, sir. Okay. Very high. Just checking. Okay. So that's the CLI. We're just going to focus on R1 and R2, which are the peers that we're going to use to establish the tunnel. Again, we're not going to focus too much on the configuration, but basically right now what we are using is just let me check what was the IP on this one. First base. We're using tunnel 1 on this one. So we're just using a normal like a basic static VTI configuration. How do I know it's a static VTI? Because of this comment here. So the tunnel mode IPsec IPv4, that's what's making it like static VTI. If it was not here, it would be just like a GRE over IPsec. The difference is just mostly with the overhead, because with GRE over IPsec we have more overhead. But right here, this is our configuration. So this is our static VTI, and the IKV2 configuration. Okay. Section crypto IKV2. So right here, this is our IKV2 configuration. The proposal here is where we specified what I would spend is the famous Hegel. So that is the encryption. We're using AES-CBC 256, and for integrity SHA-256, and for DFM Go 14, and that's where we specified what is the authentication method. So in our case, we're using pre-shared key, and it's the same key on both sides. And so, but that's just basic configuration. Again, we're not going to focus too much on this one. So what I wanted to see. So what we're going to focus on is what's happening during the establishment of the tunnel. So let me take some debug. So first of all, so if you want to verify that on IKV2 VPN tunnel is up, we can check with this comment. So that is our tunnel. We can also check the chat essay to see if I can type correctly. Check it out. Sec essay. So right now we're not setting any traffic. Okay, I was doing some tests yesterday, sorry. So that's why we have some ncaps and tcaps. So that is for the data plane. So if you want to check if traffic is being set correctly, so this is why we're checking this. And in our case, since we're using route-based VPN, one thing really important. So there are two types of VPN. There are route-based VPN and policy-based VPN. Basically, different just how we determine the traffic selector. So with route-based VPN, what we do is we create a VTI, like a virtual tunnel interface, like interface tunnel 1 or whatever the number, and we determine our interesting traffic or encryption domain based on a routing table. So this is the idea of route-based VPN. Normally it's any to any, so that's why we're saying it that way, because we're going to use our routing table to determine which traffic to send for the VPN tunnel. We can either create a static route pointing to the VTI as egress interface, or we can use dynamic routing protocol like ERGRP, OSPF, etc. Meanwhile, policy-based VPN, with policy-based VPN, we determine our interesting traffic or our encryption domain using an ACL. So basically, we create an ACL saying from X to Y, and apply this ACL in a crypto map, and then the router, once it receives the traffic from this network, we know it has to encrypt it. I believe in Cisco, in the future, they're not going to support policy-based VPN anymore. So I don't think you have to worry about that too much. So it was just so that you can be aware of that. So route-based VPN and policy-based VPN. Basically, what with route-based VPN, we're using a VTI and we are determining our encryption domain based on our routing table. Meanwhile, with policy-based VPN, we are determining our encryption domain using ACL and applying this ACL on the crypto map. So that is the difference. And again, for this demonstration, we're using a route-based VPN because we're using a VTI, right? And we're going to tell this device which traffic to send for the VPN tunnel based on our routing table. So what I wanted to share with you, what else? Another way we can check that everything is correct is, for example, we can check show crypto engine connection, and it will show us both the two chat essay and also the phase one or the init essay. But so right now, the first thing that I wanted to do is to show you the negotiation when everything is set correctly. So I'm going to enable some debugs. So since we're using IKV2, those are some debugs you can enable on the router to see the negotiation. So the first thing that we're going to see is a negotiation where everything is set correctly. And since the tunnel is already up, we're not going to see anything. So let me just shut down the tunnel and bring it back. Let's go to R1. We should start seeing something. Okay. So I'm going to maximize this one because I don't think we need the topology anymore. We're just going to focus on the logs, on the debugs. Let me just tap everything. Maybe the tunnel should already be up at this time. Maybe not yet. Let's see. So crypto, if I can type it correctly, I gave it to, let's say, still in negotiation. It's R2. Maybe I didn't change anything. Let's go to R2. Did we change something? I shut it down. Okay. No shutdown. Thank you, sir. Okay. Okay, so the first thing that we're going to see is to see what's happening on the background when everything is set up correctly. After that, we'll have some scenario we're going to change some parameters and force it to fail. Really, we should have enough information. I believe so. Did I remove the debugs? Let me just stop it. Okay, So first thing, I mean, the most important thing is to identify the first packet. So one way to identify the first packet is, first of all, as I mentioned during this training, right? The first packet in IKV2 would say like init essay, and also the first packet, the responder SPI should be all 0. Meanwhile, the initiator SPI will be like alphanumeric, but at least the responder SPI would be all 0. So let's search for the first packet, and also let's go. Let's see this one. Okay, right here. So let's start with this one. As I was saying, the first packet in IKV2, we said init essay. So this one here, essay init essay. And the first packet the responder SPI, as we can see right here, will be all 0, as we can see here. So this one here is the first packet. So we identified the first packet. And one other thing we can focus on is to know which one is the initiator and which one is the responder. Basically, which one sent the first packet? Is it this router here or the router? So one way to know that, once we identify the init essay and also the one with the responder SPI with all 0, we know this one is the first packet. One way to know if this one is the initiator or the responder is this information here. So it's saying sending packet to, which means this router is sending this packet. So since it's sending this packet and that's the first packet, then that means that this router is the initiator. So we get all our information. So this router is the initiator, sending this the first packet to the remote router, which is R2. So again, remember during the init essay, this is where they're going to negotiate the uh, the ciphers and also the fee and mango and not transversal. So that is the first packet, and that is the response. Again, it's a communication, right? So when we send something to the remote device, we're expecting a response. So how do we know this one is the response beside that? Also, you can see right here, it's saying IKSA init exchange response. So it's saying it's right here. The payload is saying it. So that is the request coming from us, which is the first packet, and that is the response. So let's see if it's complaining about something. No, it seems that everything is okay. Then we're passing the init essay. After the init essay, this is where they generated the secret key from with diffie element. So after the diffie essay, we're going the init essay, so we're going to authenticate the peer. And also we're going to negotiate the child essay. Let's see. Right here, you can see as the period is saying authentication exchange request. Basically, this one is saying its identity to the remote peer, and then right here we receive the response. And let's see what the response is saying. Okay, it seems to be fine. Right now we are authenticating the remote peer from our side. And then right here, this is where we're negotiating the child essay. As I was explaining right during the child essay, it's where we're going to negotiate the transform set or the encryption, the hashing algorithm, the encryption algorithm, and also the traffic selector. And as we're using routed based VPN, again, it's just saying anything. Local proxy, it's all 0. Remote proxy is all 0. So this port here is a negotiation where everything is set correctly. So we can use the same comment to check show crypto activity. I say, I'll just use show crypto engine connection active if we're saying both. Those are the IPs I got to try to say, and this is for the init essay. So right now we're going to modify some parameters so that it can fail. Let me just minimize it a little bit. So first scenario that I'm going to do, we are the VTI. So I'm going to shut down the VTI and this one, and let's see what's the difference on the logs. Okay, just go over here. What do I still have? No, I'll move the debugs. I have to put them back. Okay, let's see what we're getting. So again, this one here, the VTI is shut down. We can either like do it with shutting down the VTI or the physical interface. But right now what's happening is that this one is not configured, or at least there's no connectivity between the VTI to negotiate the tunnel. But let's see what's happening on this device here. So, okay, still hasn't negotiated, still using the previous one. Let's wait a little bit. Shut down. Okay, so we can see this one here is the first packet, right? And how do we know that? We can see right here the responder SPI, as I mentioned previously. Okay, it's all 0. So this is how we know it's the first packet. So this one is trying to negotiate the tunnel. Since tunnel is down, it's sending the first packet to the remote device, but it's not getting reply, which is why we're seeing those which transmitting packet here. And after a given time, we should see a message about maximum number of transmission reach, etc. But we can just wait. Let's wait a little bit. Let's just wait. After that, I will stop it and we'll go over it together. Let's see if which one's meeting, still no reply. Let's take this last one. I can just shut down the physical interface. It will be the same thing, not just here. So one thing that I want to get your attention here with this, what's happening right now, when we're seeing this kind of behavior, when we're sending the first packet, I mean, how do we know this one is the first packet? As I was saying, on the first packet, the responder SPI will be all 0. So you can see right here, responder SPI, all 0. And also remember the first packet in IKv2, it's called init SA. As you can see right here, you can see it's saying IK SA init. So we know those are the first packet. So responder SPI all 0, and also this one here is giving us the global. That's the first packet. And right now, this one is the initiator. And how do we know that? Because then sending to. So that's the first packet, and this one is the one that's sending this packet. But one thing I wanted to get your attention is when we're seeing this kind of behavior where we keep sending the first packet, and we're not getting reply, I mean, we're not receiving the response as we should. For example, we'll get like we transmitting packet error, and also something saying maximum number of transmission reach. If we wait it longer, we'll see it. Most of the time, that's because there's a connectivity issue between the two peers. So either this peer here is not able to, it doesn't have connectivity, so we can just check, for example, some normal ping, or maybe maybe there's connectivity, but the remote device is not configured to accept this negotiation. So it's like R1 is saying hola, and R2 doesn't speak Spanish, so it doesn't know how to respond to R1. So there could be multiple reasons behind that. Either connectivity issue, or the other one is maybe the remote device is not configured to negotiate the tunnel with the one that's initiating the tunnel. So that's what I wanted to point on this one here. So let me just bring the VTI. Okay, just before bringing the VTI, we're going to modify something to force a different scenario. Section crypto KV2. So I'm using the default proposal. So let me just modify something so that this one doesn't match. And we can review together what's the behavior in this scenario. So let's just change the integrity. Let's use MD5 to show only section KV2. So in this one, we changed the integrity. It was previously was SHA-256, so we changed it to MD5. But if we check in this one, let's see. So there, try to check it, but you can use this one. I can type correctly. Okay, so on this one, for integrity, we have SHA-256. So right now they're not matching, and as I was explaining, the parameters has to match for the init essay to be successful, or they have to find a match. If I give it, we can have multiple parameters like we use for this line here. It can be SHA-256, SHA-1, etc. But in this scenario, one side is using MD5 as integrity, and the other side is using SHA-256. So we're expecting it to fail, but again, we know it's going to fail. But the most important is just to see what's happening, what will happen in this scenario. So let me enable the box in this one again. And that is what the chat is here. Okay, so let's bring the VTI, open this one, no shutdown. And let's see what's happening when we're having a mismatch on the init essay. I think I already got the error. Again, we know it's going to fail, right? But the most important here is to see what the logs are saying, because it's really important to be able to first interpret the logs, and based on what the output knows, where to look or where to check. So for example, in this negotiation here, it's already started. So okay, let's wait for the next one. Okay, let's just I think we have enough information. So let's start first. As we did previously, let's identify the first packet. Even if in this one here it will be the same thing, but I'm just taking the box in one side, but it will be the same thing. So from this one, if the remote device is the initiator, we'll see something saying like receive packet. But again, since it's the first packet, the responder SPI will be all 0. Let's see. So I wanted to. So that is our first packet. Okay, that's a good scenario because this one here right now is the responder. So how do we know it's the first packet? The responder SPI, as you can see here, it's all 0. And also, remember we're using IKV2 and IKV2, the first two packets are SA init or init SA. You can see right here it's saying IK SA init, and it's a request. Which means this one here is the first packet. Right now, who is the initiator and who is the responder? Okay, the packet is saying receive packet from. I mean, that's not from us. So it's something that we're getting from the remote device, which means the remote device is the initiator and we are the responder. So the remote device sends the first packet, which is the init SA, to negotiate the VPN tunnel. And let's see what we're going to see. So we have to send a response, right? Right here, it's complaining about something. Failed to find a matching port IC. And also, let's see the response. So that is the request and that is the response. It's saying it right here. You can see IKSA init exchange response. You can send the exchange payload. It's saying no proposal chosen. So remember, during the init essay, this is what we're going to negotiate the ciphers. In this case, in router, it's a proposal, is the proposal configuration, and also the we're going to negotiate natures, but natures is being done automatically. And also the difficult. So if something is failing here, we know that it has to be something with the ciphers that we are specifying on the to IKV2 proposal. So first is to identify what's happening. And if something is not happening correctly, it's to be able to know where to look or on which part of the configuration we have to look first. So on this one here, it's depending on the init essay. As I was saying, normally in the init essay, we already know what's the parameters because I made the change while I was on the call. If we check section crypto IKv2, okay, if I can type correctly. So we know it's failing on the init essay. So we know the first thing to look for is the proposal. So let's just compare the proposal. And we can see in this one, for integrity, we have SHA-256. Meanwhile, on R2, let's see what do we have. So if I can type correctly. Meanwhile, if we check in the proposal on R2, we can see the integrity is different because using MD5. Again, I mean, I made the change while I was on the call, right? But if you get the idea, the first thing is to be able to first take the debug and be able to identify what's happening. So we know that from those logs here, it was failing during the init essay. And we know during the init essay, this is where they're going to negotiate the ciphers. And this part of the configuration is the IKV2 proposal. So if we're saying there's something is not happening, I mean, we're getting an error here, the first thing we have to check is to see if the proposal are matching. So just so that you can get the idea. As you can see, it's not matching. So let's just put it, I believe I changed it on this one. So I gave it to proposal. We're using the default integrity SHA-256. So that was us modifying the init essay. So let's play with something else. After they negotiate the init essay, the next message should be the authentication. So let's just, okay, let me just remove those debugs first. Let's just change something on the authentication so that it can also not matching section crypto. Okay, so the part of the authentication in our configuration here is this part here. This is where specifying what is the peer identity and also what is the appreciate key we're going to use. So peer tag, that is the address. Okay, so I'm just going to change the appreciate key and this one, let's say local to be Cisco 123. So right now it's not matching anymore. And crypto, okay, crypto. I mean, you can see this one here is, it has for appreciate key local Cisco 123. While if we check in this one, so owning section crypto, okay, key ring. It's saying for the appreciate key for the remote is Cisco. I mean, they're both Cisco, so it's not matching. But let's see what's happening on the logs. I mean, what the logs are telling us when we're having a problem of the when there is a mismatch on the appreciate key. On debug, crypto, okay. Again, the idea is here is just to be able to identify first what should be happening and what is happening, and based on what's happening from the logs, where do we have to look first, or what do we have to search for? What do we have to search first? So, did I shut down the tunnel? I don't think so. The first tunnel one, just first in negotiation. I don't want to. Okay. Let's see what's happening when there's a mismatch on the pre-shared key. Okay. I think that should be enough. Okay, we'll do the same thing. First, identify the first packet. In this case, on the first packet, the responder SPI should be all 0. Where is the responder SPI? Where is the first packet? First packet. Okay, so for this negotiation, this one here, let's say that's the first packet. And how do we know that? The responder SPI all 0. So it's saying here, SA init exchange request. So this one here is the responder because they can receive packet from and not sending packet to. So that's the first packet coming from R2, which is trying to negotiate the tunnel. So that's the init SA. It's not complete. Let's see. Let's scroll down. Okay, maybe we have two negotiations. So not this one. See, receive packet from this one. Oh, the tunnel was already up. Not this negotiation then. That's our exchange. Okay, here's the negotiation we're looking for. So we're sending the response. So this part here, the init SS will be correct because it's matching on both sides. And again, right here, you can see it's a completed SA init exchange, which means that everything is correct as part of the ciphers. Right now, we're receiving the authentication exchange request. The human end is the initiator, so that's why we're saving this first packet here. I mean, the human end is setting its identity, and we're going to search our database to see based on the identity what is the keyring that you're using. So in this case, we're using tag. The tag keyring is able to authenticate the peer. You can see right here. So we get the correct identity, but the authentication was failing. So you can see right here, right? So we complete the init essay, but it's failing during the authentication. I mean, once we see this message, we know that it's failing during the authentication. Then we know like the first thing we have to check, for example, is the keyring, because we're not using RSA signature. So if we're using RSA signature, maybe we'll have to verify the identity certificate of the remote peer, and also if we have the certificate of the CA, also install this one. So one of my colleagues will give a training about PKI, so you don't have to worry too much about RSA signature if you still do not understand it. But right now we're using pre-shared key. So basically, since we're using pre-shared key, the first thing we have to do is to check the configuration for the pre-shared key. Why we're doing that? Because during the we're saying that the negotiation is failing during the authentication, which means something is wrong either with the pre-shared key or with the identity. Let's see, and we already know what's the problem, right? Because I made the change on the call. So basically, what the problem is that from one side, both keys are Cisco, and this one I believe I changed it to Cisco 123. Again, the idea is just to be able to interpret the logs and based on the output to know where to search or what's first thing you have to check again, because that's the idea of all troubleshooting. So we change this one, Let's see what is. So our last scenario, we're going to modify the transform set and see what will happen. Which one do you change it? Maybe it's an auto. So let's go back to auto. Okay, I think we change the pre-shared key. Just just put it as it was. Okay. So crypto. Okay, so it's set correctly. It's the same. Right now, let's change something different. So instead of changing the something to force the index to fail or the authentication to fail, let's modify something so that the child essay can fail and that we can see what will happen or what will the logs tell us. Look, what am I checking? If I can type it correctly. Okay, so we're using this transform set, which using as encryption AS256 and HMAC SHA-256. Let's just play with that one here. So I'm going to use the same command, crypto IPsec, the name. So instead of AES, let's use this, for example. You don't have to pay too much attention if you do not know where to configure that. Again, the idea of the session of this demo is that it's not really about the configuration, but to be able to interpret the logs and based on the logs to know where to look. So if there are some comments that I'm putting here and you don't know what it means, that don't pay too much attention to that. You can always Google to find like a configuration guide, right? But I think the most important here is to be able to identify what should happen during the tunnel negotiation, and based on the output, what is the first thing you have to look for. So this one is tunnel 1. Let's just shut it down. I don't want to wait. I believe I have debugs enabled. If I can type correctly. Okay, have to be slower. Okay, no, I don't have. Maybe sick. Okay. So that will be our last scenario. So basically we change the transform set, which means that the child essay should fail. Let's see what will happen or what will the logs tell us when there's a mismatch on the child essay. Okay. Okay, I believe we have enough information. I don't need more. So let's search for the first packet. Not yet. Remember on the first packet, the responder SPI will be all 0. So this one here. So that's the first packet, and based on this output, we are the responder because it's saying receive packet from and not sending packet to. So this one is the first packet because responder SPI, as you can see, is all 0, and also it's saying init essay or essay init. As we know, with IKV2, the first 2 packets are init essay. So this is where they're going to negotiate the ciphers. Let's see. So that's remote PA sending us the first packet. So this part should be okay. So that's us setting the response. As you can see right here, it's saying IKSA did exchange response, and you can see also right now the responder SPI is not all 0. I mean, it's alphanumeric. So that's us sending the response, and we can see completed essay init exchange, which means the ciphers are matching on both sides. After that will come the authentication. Okay, authentication or exchange request. And then, okay, we find the correct keyring to authenticate the peer, and it seems that everything is matching. Okay, then after that, we'll expect the child essay. Okay, so here's the child essay. Again, using remote route-based VPN will be the proxy will look that will look that way. The proxy, local proxy and remote proxy, that's the what is called like traffic generator encryption domain, which I already mentioned at the beginning of the session. Basically, just a way to tell which traffic are we going to send for the VPN tunnel or which traffic to encrypt. Okay, so this port is matching. As you can see right here, you can see right. Also, we're getting this first one here. Transform proposal not supported for identity when failed to find a matching policy. I think that's the most important part. And again, why is that? Because as we saw previously, right, I modified the transform set. So if we think like the init essay is being completed correctly, and the authentication is also being completed correctly, but during the child essay, we're getting some error. So the first thing we have to know is that we don't have to check the proposal, because um, the proposal is mostly for the init essay, right? So if we're passing init essay and we're passing authentication, so you don't have to check the proposal or the keyring or the certificates if we're using RSA signature. What we have to check is the first, for example, we can check the transform set, or check if one of the side is using PFS and the other side is not using PFS, or also check a, what I want to check, show crypto, sec transform set. Check the transform set. For example, this one, we're using the transform set tag. We specify that part of the configuration from the IPsec profile. Okay, it's taking longer. So within this profile under the VTI, and you can see this profile is using the transform set tag. So this is how I know we're using this transform set tag. And in this transform set from R1, we're using AES 256 and SHA-256. And as you remember, I changed that on this part. Let's say do show. So IPsec, oops, transform set. We're using the same transform set. As you can see here, it's not matching, right? Because one side is using ESP this, and the other side using ESP AES 256 again. So if something's if we're getting an error during the child essay, the first thing we have to check is this transform set, and also to see maybe if one side using PFS and the other side is not using PFS. And also something really important, sometimes that can also cause problems. So for example, on this one here, you can see it's using tunnel mode. So if maybe the ciphers are matching, but this one is using tunnel mode and the other one is using transport mode, that can also cause problem. So in our case, they're both using tunnel mode. As we already know, the problem is just with the with this cipher here. So right now we're using ESPS 256, and in this one using ESP this. So that's a problem. But again, the most important point here is to first be able to see the logs, and based on the output of the log, know what to check first. So that was the idea of this troubleshooting demo. So first we changed the we forced the tunnel to fail due to a communication problem, right? Which was our first scenario, and then we modified the one of the proposal, one of the encrypt. I think we modified the hashing integrity so that the int essay can fail. Again, when we're saying init essay fail, you know what should be the first thing you should check. And then after that, we change the pre-shared key in one of the sites so that it can fail during the authentication. And this last scenario here, what we did, we just modified the transform set. So I can put it back as it should be. Let's see, should have the comment. And once we have the same transform set on both sides. Okay. See. So we give me some. ESP, yes, 256, 256, ESP. So right now the tunnel should come up correctly at the first tunnel one. I just I don't want to wait, so that's why I'm shutting down the VTI and bring it back. You can either check if I can type correctly. I think I'm too quick for my keyboard. Show crypto engine connection active. I can type correctly. So you can see now to IPsec chat essay, and that will be for the init essay. So the tunnel is up right now. So, if I can type correctly. Oh, if you want, you can also check the IPsec. Okay. So crypto IPsec essay. Oh, in other test, we can also ping the VTI of the routers. Show IP interface brief. Let's say this router is using, okay. So let's try to ping 169.254.0.1. Okay, so if we check the Shokuta IPsec essay again, we should see ncaps and decaps. So those are the ping. So right now the tunnel is working fine. Again, the idea of this one is just to be able to read the logs and based on the output of the logs to know what is the first thing we should check. So that was the idea of this demo. So I'm going to stop it. Again, I use GNS3. So if you're familiar to GNS3, you just have to download the Cisco image. Again, I'm using free routers. And the routers are those one here. So you can just download some Cisco image and then simulate the lab if you want. So that will be all for the demo. And as a summary, again, as we were saying at the beginning, IPsec is an architecture that describes how to protect IP traffic over an insecure network like internet. And the protocol used to create a secure connection between peers is IK Internet Key Exchange. They are IK version 1 or IK version 2. IK version 2 normally use 4 packets for all the negotiation and is considered more secure than IKv1, as we mentioned at the beginning of the session. And also, sites at VPN tunnel leverage IPsec to provide confidentiality, integrity, anti-plane authentication. You can already go over confidentiality, but as I was explaining, confidentiality refers to the fact that data is encrypted and that only authorized user is able to see this data or access this data. Meanwhile, integrity is just a way to prove or to verify that the data hasn't been corrupted or modified in the past. And as far as anti-play, this is just a way to see if we it's just a way for the device to determine what traffic that we receive in order to avoid to receive the same traffic twice. Let's suppose that we already receive traffic with a sequence number and another device, maybe someone is doing man-in-the-middle attack is sending this packet if it has the same SPI, the same sequence, so then we're not going to accept it. And the authentication is just a way to prove ourselves to the remote device. In the case of satellite VPN, we can either use, with IKv1, we can use pre-shared key or RSA signature. And with IKv2, we can use pre-shared key, RSA signature, EAP, etc. And that would be our session for Q&A. If you guys have any question, you can go ahead and ask me, and I'll try my best in order to answer those questions. I don't know if you guys I don't know if you guys have any question. Or if you want, you can still ping me if you have. After this session, maybe you have something was not clear, or if you have any question, you can ping me directly, and I will be more than happy to answer you without any problem. But if you guys do have question, you can go ahead and ask me.